next session, I'll be going over how to add data to RMG and going into a bit more detail about how RMG-database is sort of designed or organized, and what steps you would go through to add more data to the database to improve your models. So this morning, Lawrence talked about and Jim as well, talked about the overall process of how they approach to improving models. This is more on the technical side. How do you actually add your improvements to the database? So I guess to start, just to give you an idea, so this is analysis of the methane oxidation model that Jim showed this morning, and to give you an idea of what fraction of the parameters are from known sources versus RMG estimates. And as you can see, in the core, a decent fraction is from literature. So these are what we call exact matches in RMG. So there's some input piece of data, whether that's Thermo or Kinetics, and then we're using it as is for our model. And then the blue half is the estimate. So some average of what we know applied or extrapolated to something we don't know. But in the edge, you see that the vast majority are estimates. And because we're looking at thousands of different reactions, and then there's only a very small fraction of those which are studied. So that's why in our general process, we'll run a model, and then we'll do the sensitivity analysis to figure out which of these is actually important for our system, and then we try to improve those. And in terms of software, so this morning I mentioned Arcane during when going through the RMG website. So this is just to give you an idea. We have all these names of softwares to give you an idea how it all fits together. So RMG is here in the middle. We generate the mechanisms. When we want to improve data through quantum calculations, we'll start with some electronic structure software. This can be Gaussian, QChem, MoPro, Orca. There are dozens of them out there. And we'll run a calculation for some structure, and then that will give us all the details of this electronic structure, such as energy, frequency, etc. And then that gets put into some software to actually give us a phenomenological rate or thermal value. And this includes Arcane, which is part of RMG. There's also other software out there, such as MES, Mesmer, Polyrate, Multiwell. Again, like half a dozen or more different softwares to do this calculation. And then this gives us something that we can actually use, Thermo rates as a function of temperature, or rates as a function of temperature and pressure, which we will put into RMG to generate the model. And then from RMG, once you get the mechanism, we'll put into some simulation software. So this will actually be covered in the session following this. So how to simulate your model in Cantera or RMS, which is the reaction mechanism simulator. And we also have, or there are also some packages which try to streamline that first half of electronic structure calculation, such as ES2KTP, ARC, which is developed in our group, AutoTST, mainly in Professor West's group at Northeastern. And they automate this entire process of doing the electronic structure calculation and getting the rate out. Right, so this is the overall map of all the software that is involved in improving our models. Are there any questions? Okay. So now going into RMG-database. On the left there, I have more or less a list of all the data sources that exist for thermal imaging kinetics primarily in RMG-database. And then here I rank how easy it is to add data and whether or not it improves other estimates. So by that, I mean if you put in a piece of data for one species, for example, it's not going to help you get better thermal for another species. But if you put in a group additivity value, then that could improve a wide range of species. And similarly for kinetics, if you put in a library entry for a specific reaction, that will only improve that one. But if you put in a training reaction, which I'll go into a bit more later, that can improve it for a whole series of similar reactions. So now just going through this list, for thermochemistry, we have these libraries, which are very easy to add things to, but again, they don't improve other estimates. Adding new group additivity values is more challenging, but with the benefit that it does improve other estimates. We have the QMTP functionality in RMG, which runs on the fly quantum using semi-empirical methods, which is sort of irrelevant in terms of adding data, but again, it doesn't improve other estimates. And then the recently added machine learning estimator is very difficult to add data to, but we don't have any sort of framework for adding data as of right now, but it does have the potential to improve a large set of estimates. And then for kinetics, we only have libraries and families, libraries being for specific reactions, so it's very easy to add data to libraries, but it doesn't improve other estimates. And then families, if you add training reactions or adding families, it can be more challenging, but again, you improve other estimates. So we'll go through these one at a time. So for Thermo libraries, these are probably the easiest thing to add to RMG if you want to improve Thermo data for a specific set of species. So it's located, again, in RMG-database, input Thermo in the library. And these are all single Python files. So for each so-called library, there exists a single file in the database. And if you want to add a new library or add entries to a library, you can manually add them by just copying and pasting like the syntax and then changing your values. Or we do have this import chemkin library.py script, which exists in RMG-database. And to use this, you basically need a chemkin file and then a species dictionary to identify all the species in your chemkin file. And then if you run this, it will automatically create a Thermo library for you that's properly formatted. And the requirements is you need to have the structure and its corresponding Thermo data. And this is a snippet of what a Thermo library looks like. So we have some metadata, the name of the Thermo library. You can add descriptions, which is optional. And then each entry in the library looks like this. It has an index and a label for identification purposes. You need to put in the structure of the molecule using an RMG adjacency list. And then you have your Thermo data right here, which can be in any of the Thermo formats that RMG supports. So here we have Thermo data, which is just a list of CPs, the H298, F298. Alternatively, you could have a NASA polynomial here as well. And I think if you use the import chemkin library script, since chemkin files list NASA polynomials, you'll get NASA polynomials in your library. Right. So this is basically it. If you want to manually add, you can just like copy paste these entries. Generally, importing chemkin is a bit easier if you have a bunch of values. Right. So then group additivity. It's also located in Thermo under the groups folder. So groups are also single Python files, but they're already pre-organized into various types of group corrections. And if you want to add data, then you can either add completely new groups or update values for specific groups. But it's a bit more difficult because you have to fit these group values beforehand, which I won't get into in this talk, but you need to have some amount of training data and you need to fit these group values. And then to add it to RMG, you need to define the structure of your group and also update the group trees correspondingly. So these are the files that are in that folder, thermo/groups. And I went over this a little bit when talking about going to the RMG website this morning, but we have different classes of group corrections. So the base groups, and then all these radical corrections, ring corrections, etc. So then you would determine which type of group you want to add based on your molecule. And then a group entry looks very similar to libraries, except we have, instead of a molecule adjacent to this, we have a group adjacent to this. And for groups, it's important that we have this label, which is just an asterisk, which denotes the atom that this group applies to. So basically, when we estimate molecular thermo using progressitivity, we'll go through all the atoms, and then each atom will have some group that it matches. So in this case, we would match to this group based on this atom rather than any of the other atoms. And then the other atoms sort of describe the environment around the main atom. And then you have a thermal data format contribution to the overall thermo. Are there any questions? And then skipping over QMTP, again, for the machine learning estimator, all the parameters are located in Thermo/ML. And by parameters, I mean we have a set of, or a definition for the neural network architecture that it relies on, and then a set of weights for all of the different layers in the neural network. And if you were to want to add data, then that would entail adding data to the training set and then retraining the entire network. And I think the retraining takes like a couple of days based on like the complexity of the network and how much data we have. And so if you really are interested in improving this, please contact us or specifically call in, and then we can talk to you more about that. Right. So this is it, basically it for Thermo. So in general, in our group, as you're improving a model, the first thing is always to add library values for Thermo that is either uncertain or that are very sensitive in your model. And and usually that's quite sufficient to building a model. Groups are harder to improve because you do have to have a lot of data to actually fit like a single group value. And we do some of that. So Lawrence, I don't remember if he talked about it in his talk, but he has been fitting improved group values for some aromatic chemistry. And then for that, he will calculate dozens of molecules and then fit like one or two groups on the path. Okay, so now moving on to kinetics. So kinetics libraries, idea is similar to Thermo libraries. These are now located in input kinetics libraries, which makes sense. So for kinetics libraries, we do support subdirectories, which you might notice during when we browse through the database on the RMG website. Some of the library names have a slash in them, so it helps us organize them a bit. And for these, the format is a bit more complicated. So we have a reaction file, which is in Python syntax, and then RMG species dictionary, which you've probably seen a couple of. And here, adding data, again, is either manual or using the same import chemkin library script. So when you use this script with a chemkin file, if you have both thermo and reaction in the chemkin file, then it will create both a thermal library and a kinetics library. So it sort of does everything at once. And again, you just need your structures and your rate parameters. And so the reaction file looks like this. It's basically a list of reaction entries. So here, the label defines the reaction, and each of the species names has to correspond to something in the species dictionary. Right, and then you need the kinetics, either in any of these formats, basically, that RMG accepts. So it could be Arrhenius, or if you can also have pressure-dependent kinetics. So that might be PDF Arrhenius or maybe Chebyshev, as well as these other pressure-dependent forms. And then the dictionary, which you've seen, is just the label, which has to match its label in the reaction, and then the RMG adjacent to it. So this is actually the bulk of the talk, or almost. So adding Kinetics families is something that we have to do occasionally. It's not very common. So I mentioned we have 60 Kinetics families now. We have most of the important chemistry for sort of combustion high temperature systems covered. But if you want to model something that's sort of a bit out of the scope of what RMG can handle currently, it's possible that there are new types of reactions that you might need to add. So a reaction family or Kinetics family is defined by a groups file, a rules file, and then at least one training depository. And right now there's no script to help you make a Kinetics family. It's basically you have to write them manually. And we usually do that just by copying an existing family and then adjusting it. And then the requirements, you need the reaction recipe, which defines how the reaction actually occurs, and you define group and tree structure, and adding training reactions to actually provide data. And in some cases, you might need RMG pi modifications. So if you actually want to add a Kinetics family, then I would recommend talking to us to get a bit more guidance on that. So in the Kinetics family, you have a groups file, which defines most of the important information for the family. So for example, we have this reaction template line, which defines the groups that are involved in the reaction and then the product. And then so each of these entries corresponds to a group. So for example, here we're saying that this is radical addition to a multiple bond. So our template has this RR group reacting with the YJ. So RR is here. And so this is actually just a generic multiple bond. So any two atoms connected by double, triple, or benzene bonds. And then the YJ is actually radical. So basically that defines the template for this reaction. The reaction recipe defines the steps involved. So you can see for this reaction, we're going to change a bond by decrementing it by one order. So basically changing the double bond to single bond, for example. And then we form a new bond to the radical, and then the radicals changes places. So if you want to define a new family, you would write out the recipe for whichever changes you need in your reaction involved. And then, right, so with your recipe, you write out the templates, and then, I don't think, right, we have to include this, but at the bottom of the file, there's actually a tree structure definition. So basically, in our Kinetics families, these templates are at the very top, and then you can define more specific templates that are sort of that expand this tree. And that's so that when we're estimating a Kinetics for a reaction, we'll take the actual molecules and descend this tree to find the most specific thing that we can match. And then in that way, we can get kinetics that are very relevant for that specific species. So if you're making a brand new Kinetics family, you should add some groups depending on how much training data you have. Yes.
So I guess if you have a reaction that you want to add as a family, and you're not sure if it's already part of a subfamily of one that already has files associated with it, is there a way to sort of probe the database and try and figure out where it fits, or if it fits multiple places, for example?
Right. So, so the question was, if you have a reaction you're interested in, you want to see if there's already a family that exists for it. So the best way is to go onto the website under Kinetics search and search your reaction. And if it comes out with 0 results, then that means most likely there's no family for it. Another way is to use the script that I'm about to talk about for training reactions, and that will also do a similar thing where it sees if it matches any of the existing families. So that will be in like 2 slides. Does that answer your question?
Sure, yep.
Okay. Right. And then there's a corresponding rules file, which actually has the rate rules for the family. So these are the actual data that are used to estimate the kinetics for a reaction. So right now, we've actually started to move away from hard-coded rate rules, instead favoring sort of on-the-fly creation of these rate rules. So now this file is less important. So if you're creating a new family, you actually don't need to have anything in this file, although you need, the file has to exist still right now, but it can be empty. Right, so training reactions should be used instead, which yes, is now, I'll talk about now. So training reactions are what RMG uses to automatically create rate rules in these kinetics families. So when you run an RMG job, the first thing that will happen is that we'll take all the training reactions, and go into the family, see which of the templates it matches best, and then assign its rate to that template. So then, if we have a new reaction that we're estimating, and we go fall to that template, then we'll use that rate that we originally trained into that. So the training reactions are located under each family in the training folder, and its format is one reaction file and one dictionary, which is very similar to the Kinetics library. And to add data, we highly recommend using this IPython notebook. So this has greatly streamlined the process of adding these training reactions before you have to do it manually. And requirements, again, you just need to have the species structures and rate parameters, and you should create an RMG Kinetics library first, which is basically the input to this IPython notebook. All right, I said most of it. So yeah, so they're very similar to Kinetics libraries. The key difference between a training repository and a Kinetics library is that you have to label the reacting atoms. And by label, I mean adding those *1 and *2. Actually, I don't think I showed that. But there are these labels that we assign to the atoms to tell RMG that those are the reacting sites. Oh, I guess, so it corresponds to these, yeah. So these *1 and *2 are the labels, and they tell RMG that these two atoms are the ones that are reacting according to this recipe. So for to add training reactions, the reacting sites have to be properly labeled in accordance with whichever family you're adding them to, which is a big reason why using the notebook is recommended, because it automatically labels all that. Right. So in order to add training reactions, we just use the IPython notebook. So are there any questions before I switch to the demo? All right. So this is the notebook. It's located under RMG-Pi, IPython, and then Kinetics library for training. So we spend a lot of effort trying to make this easy to use, since this is a recommended way to add new training reactions to the database. So yes, there's some description up there, and then basically this section is the only section that you need to provide input to. So as I mentioned, you need to first create a Kinetics library from your reactions. So you'll put here the name of the library you want to add as training reactions. And so in libraries, you can put whatever types of reactions you want. There doesn't have to be a family for it. So if you're interested in some particular reaction, you want to see if there is a family for it, you can just make a library from it and then try the script. And then here, you can set which families you want to add training reactions to. So if you don't know what families you're interested in, you can just put all, and then it will load all of the families. Or if you're only trying to improve a particular family, you can put that here. So here I've just listed 3 sort of semi-arbitrary families. And then the script will automatically compare the kinetics between the new reactions you're about to add and what RMG would have estimated previously. So you can get an idea of that. And this show all determines whether or not this script will display the library reactions which don't fit into a family that you specified. So if you want to see it, your reactions, if there's a family corresponding to your reaction, you might want to leave this true, and then specify all of the families. So yes, these 2 are less important in general, so you can probably just leave them as your defaults. So you would run this block and the imports, and this block loads a database, which I've already run because it takes a little time, but it just loads the entire RMG database for the families and libraries that you specified. So then the main part happens here. So this process reactions block. So I'll just run this, and it will give you this output, which contains 1 entry for each of your library reactions, and then some details about the family that it matched. Okay, so going through this, here's 1 entry here. So we have the source library, which is just the library that you provided, a drawing of the reaction, reactant product smile, and it tells you that this matched the R-addition multiple bond family, and it matched this template, which is the set of groups that most specifically match to these reactants. And then here, it gives you the drawings for those groups. So basically, we know now that, so it matched CBH, CBH, which is this group, and this is just 2 carbons that are in a benzene ring, and then with 2 H's attached to them. And then this radical group, which is just a methyl radical. So C with 3 H's, which actually matches exactly to our reactants. And then it gives you this plot of the new kinetics from your library versus the current kinetics. And in this case, this chain reaction has already been added. So we'll see that there's actually no difference between the new and current rates. Any questions so far? Okay. So then, in some cases, for this example, I only selected these 2 families, right? So for this library reaction, it tells me that there's no matches within the selected families, and we can see that it's because this is a hydrogen abstraction reaction, which is a family that I didn't include. So then the script will not add this as a training reaction in this case. So in some cases, the library reaction might be written in the opposite direction from how a family is defined. So it will tell you that here. And the key point of this is that this plot then is actually not correct because we are plotting the kinetics as given. So then these 2 rates are actually for the reaction in opposite directions. Yeah, so that's just sort of a warning. Right, so we'll do this analysis for all of the reactions. In some cases, we have, so for unimolecular families, it's common to have 3 templates. And in these cases, so this is intra-R and endocyclic, which is sort of an intra-cyclization reaction. So we have these 3 templates, and we'll actually also output the merge template. So we'll put these templates together, and then this merge template should match your reactor. So that can be helpful to see how well this group matches. Right. So then in this case, it seems that we didn't. This reaction hasn't been added to training, and we can see that there's a difference between the current RMG estimate and this training reaction. Right. Okay. So generally, after you run that box, you can review all this output to see that whether or not it found appropriate families and templates for each of your reactions. And then once that's done, these are 2 optional steps. You can review reactions that are about to be added. In some cases, there might be some reason that you don't want to add a particular reaction. So, for example, we saw earlier that this first one has already been added. So we might say that we don't want to add this. So you can indicate that here, so on and so forth. Or if you don't want to do that, then you can continue to the final review of reactions to be added, and just take a look, double check these are all reactions that you want to add, that the rates are inputted correctly. And then once you're sure and you want to add, then you just run this last block, and this will automatically write everything to the database with proper labels. Right. And you can see that it's adding to our addition multiple bonds. It added 6 new reactions, and then I don't know why this is hidden. So normally this block should be very fast. You already did all the analysis up here, and then it should just be writing the file. I'll look into that. But usually this should be very fast, and it will write your reactions to the database. Okay, this is a little bit hard to see. Right. So then here I'm in RMG-database, and check good status, and we'll see that the training folders for RMG or for our addition multiple bond have been modified. And you can see that it added these entries. Yeah, and it will comment that it's from some Kinetics library and which entry that it's from.